In section 4.2, we're going to talk about events. Now, I've already defined event and sample space in prior section when we talked about probability basics. So I have a couple of reminders on something that we've already discussed. One of them is event. The other one is the notion of sample space. So if you recall, events are collection of outcomes or a single outcome, which are defined by the person conducting the experiment or the researcher. Now, the sample space is where all possible outcomes are, but events are defined by an individual. Okay. So in this section, we're going to take a look at a formula, if you will. This is going to be the addition formula of probability. Okay, now with addition formula of probability, what we're interested is in trying to finding probability of event A or B will occur. Now, what do we mean by event A or B? Event A or B, that means all the outcomes that are in A or B or both. Okay, so remember, they could share it together. Now, the use of or I have, as you can read here what I have, we use or in its inclusive form. There are two forms of or. We have exclusive or and then we have inclusive or in our everyday language. However, in everyday language, we use or in its exclusive form, right? So, for example, do you want to go to the park or you want to go to the movies? So it's pretty much a choice between the two. In the field of probability, we use it in its inclusive form. So the answer to would you like to go to movies or would you like to go to the park? The answer would be both. You could choose both of them actually. So this is the inclusive use of or, and that's how we use it. Two events, if they don't have any common outcomes, are said to be disjoint or mutually exclusive. So again, mutually exclusive or disjoint events are those that share no common outcomes. So in my example, I have, let's say, set A is made up of digits 1, 3, 5, and set B has elements 2, 4, 6. So as you can see, there is no shared outcome between the two sets. Therefore, we can say the two sets are disjoint or mutually exclusive. Events that are mutually exclusive could not happen or could not occur together. Okay. Next, we're going to talk about the intersection of two events. The intersection of two events. Notationally, we use A and B to show that intersection. So the keyword here is and. With union of two sets, the keyword is or. So up here I have or. That's indicative of the union of two sets. The semantics of A and or are extremely important in probability. It literally changes the interpretation of the event. So, when we talk about intersection of two events A and B, now we are interested in outcomes that are shared by both. So these are shared outcomes. That means the two events must have common outcomes. If they don't, that's fine. It's just their intersection holds no common outcome. So in my example, again, that I have right up here, set A is 1, 3, 5, set B is 2, 4, 6. What is the intersection? What is the commonality between the two sets? Well, they share no common outcome, so therefore, their intersection has no common outcome. Now, once we define these union intersections, and in the latter part I have the not E, these kind of events, what we would like to do is we like to, for any event, once we define an event, we would like to assess or find the probability for that event. So that's kind of where we're going with this. As I have it, event not E, this would be the outcomes that are not in E, but they must be in the sample space. Okay. And that would be event not E. Now we can show this association, this relationship between events using a Venn diagram. And I have here a reference for you. It's named after British philosopher John Venn. Okay, so the time frame was actually late 1800 when he came up with the idea of these diagrams. What Venn diagrams do, they simply show the relationship or association among events or sets. So they're used quite a bit in sets, mathematical sets, computer sciences, and even businesses. They use this, enterprises use it for organization charts to kind of look at the functionality of each division within the organization and then see if there are overlap of tasks and so on and so forth. Okay, so these are the Venn diagrams for them. Not E, again, notice the shaded area here is going to be all the outcomes that are in the sample space. The box you're looking at, this is square box, this is the sample space. Okay, that is like the universe that we're looking at. Okay, and the one in the middle shows you A and B. That would be the intersection of the two sets in this case. And I can write it as I'm trying to use my pen to write on this, so hold on for a moment. Okay, so I'm gonna write A and B as the intersection. Using the intersection notation, I can write this as A intersect B. Now the A or B is written as A union B. Okay, that's just the notation. Not E, there are different notations. Usually you can go like that for not E. Some put a bar on top of it, and those are the most common notations for not E. So there you have it. Now let's take a look at an example here. So in this example that I have, let's say we have two events A and B. These two events are defined as A is mammal and B is human. Okay, and we want to know if these events are disjoint. Okay, and then we want to know what A union and what A and B intersection B are. So think about this one for a moment. Let's see. Humans are mammals. Okay, but mammals are not humans. The whole category of mammals encompasses a lot of different species. Therefore, because all humans are mammals, therefore there is a common outcome to both sets, right? Therefore the two are not disjoint because I'm a mammal. Okay, so the events A union B means those that are A or B. So the choice of mammal or human, that intersection of those two is going to be mammal, right? Because humans are part of that. They're not disjoint. And if I look at the intersection of A and B, mammals and human, the intersection of those two events is going to be human. That's the common outcome to both events. Okay, so a simple example, but I thought that would be interesting. Rather than working with numbers, we just work with words in this one. Now let's take a look at the addition property. Again, we have two events A and B. The union of two events is what the addition property is defined as. So to find the union property or the union of two events, then according to this formula, we add probability of A plus probability of B, and then we subtract probability of A and B from it. And that's the general form. Now, if two events are disjoint, then what we need to do is simply drop the intersection and we get this easier version of this formula. Now, if I do a Venn diagram for this one to kind of show you how this works. Let's say I have events A and then I have event B here. So once, let's say the first part of this formula, probability of A, that would give me the circle of A. And then with probability of B, when I add to it, I add circle of B to it. Now, if you noted, the region of intersection, which is this region right in here, was picked up twice. So for that reason, we subtract probability of an A and B to remove the layer of intersection. Let me draw this a little bigger so you can see better. So this is A and this is B. Here's A and here's B. This is a circle of A and this is a circle of B. And there you go. See the crosshatch? This is A and B. Those outcomes were picked up twice. And because they were picked up twice, we need to subtract one layer of those outcomes away from it. Now, the general form is what this is, but a special case of that would be the addition rule for disjoint or mutually exclusive events. And in this case, if the two events are mutually exclusive, then the two circles of A and B are clearly apart. They have nothing in common, right? So we simply add those two regions or the outcomes in each of those events. All right, now let's try this formula. Let's say we are given probability of A is 0.28, B is 0.72, A and B 0.6. We want to find the intersection. So I'm just gonna, it's a matter of plugging them in right into the right formula, and I did. And this way we get probability of A and B to be 0.4. Right, you add these two numbers and then you subtract 0.6 from it. The sum of these two end up being 1. Right, 20 and 72% add up to 1. Subtract 0.6 from it and you get 0.4. Okay, so let's say in this next example, I'm going to roll 2 fair dice. Roll 2 fair dice. Now we're looking at regular dice, okay? The usual digits on a dice. These are 6-sided die. 4, 5, and 6. There you go. So these are again 6-sided dice. Each die has 6 sides because it's a cube. Okay. And let's say I want to find the following. I want to find probability that the sum of the digits on the die is going to equal to 10. And then it's separately, what is probability that the sum, let's say, sum will exceed greater than or equal to 11. Okay, so let's actually draw the sample space for this one and see how it turns out. One way we can write this, rather than just listing all possible outcomes, I'm going to actually draw this for you. This two-dimensional sketch is going to help us understand this a little easier. So I'm just going to call this die number 1, and this is going to be die number 2. Okay, and here are the things that could happen. These are the possible outcomes for die 1. 1, 2, 3, 4, 5, 6, and same outcomes 2, 3, 4, 5, 6. Okay, so that's what could happen. Now I can actually show each possible outcome using a dot here. Okay, so for example, this first dot means 1, rolling a 1 on the first die and 1 on the second. The dot I'm putting just now, that's when you roll a 2 on the first die and 1 on the second, and so on and so forth. So notice for each choice of the digit for each die, you have 6 choices for the second die, right? So if I roll a 4 on the first die, then I have actually 6 options of the other 6 digits that I can roll with the second die. And then here, so this would be the sample space for this exercise. We have all possible outcomes actually listed here. So there's going to be 36 outcomes in all, right? 6 by 6. Now, think about how we could roll a sum that would be 10. To roll a 10, that means I have to roll like a maybe 4 on the first and a 6 on the second one. So this would be a favorable outcome. Or I could roll a 5 and a 5. That would be my second favorable outcome. And I could roll a 6 and a 4. And there you go. So those are all possible ways I can do this. Therefore, probability that the sum of the digits is going to be 10 is going to be 3 out of 36. That's 1 in 12 chance. Of course, you can convert these to decimals or percentages, right? Now, let's take a look at the second one. And actually, for this one, how did I use the addition rule in this one? Well, probability of sum equal 10, that means probability that the sum is 10 or 11, or actually, no, that's just the sum is 10. Those are, I just counted. I did not use the addition property in this one. I will in the next one. So let's take a look at the second part. Now, probability that sum is greater than or equal to 11. So that means probability that the sum is 11 or greater than 11. 12 is a possibility, but no 13, right? Because we only have 6 and 6 maximum on either die. On each die, we have a maximum of 6 for the digits. So there you go. Here's the presence of or. Now, because you could not roll, when you roll, the sum is 11, cannot be 12, and vice versa. Right? If you roll a sum of 12, it cannot be 11. So these are disjoint events. Each of these are disjoint. So using the mutually exclusive events, that's probability of 11, or that the sum is 12. Now, probability that the sum is 11. How can I get the sum of 11? Well, just the way I did it, to get an 11, you can do a 5 and a 6. Or you can roll a 6 and a 5, right? So there are two favorable outcomes. This will give you a sum that's 11. To get a sum that's 12, there's only one favorable outcome. There's only one outcome in that, for that event, that the sum is 12. So the probability is going to be, in this case, 2 out of 36 plus 1 out of 36. And again, that's going to be 3 out of 36. Pure coincidence, that is the same as the one above. Just turned out that the number of outcomes are the same. So you can see how this works out. Now, I can do this one. What is probability that the sum is not 12? Now, not 12 means everything else, right? So this would be 1 minus probability that the sum is 12. And that's 1 minus 1/12. And that's going to be the probability of that, which is 11/12, right? So highly likely event. And so this is just another example with using the addition law. Now, let's see, did I do disjoint? Okay, let me do one. What is the probability that the sum is 8 and 10 at the same time? Again, you got to think about if that's even doable. Can that even happen? Can I roll an 8 and a 10? So, for example, if I roll a 5 and a 3, there's no way I can roll a 10 if I rolled an 8, right? So this one, there is no common outcome here. Probability is 0 because there's no outcome favorable to this event that I have defined. So let's see. Let's take a look at one last one. What is probability that the sum is odd? The sum is odd and prime. Okay, so we're looking at now the condition of and with this one. Okay, Okay, so let's actually list what are the odd sums. So the odd sums, that means the sum could be the lowest is 3, right? That's when you roll a 1 and a 2. So that's odd. We could roll a 5. We could not roll a 7, right? Because again, oh, actually no, I'm so sorry. We could. The sum could be 7. Sure, we're good up to 12. So 7, 9, 11. So those are possible sums. Okay, the sum could be that. Prime numbers. Well, prime numbers in this list. Remember, 1 is not prime. So I'm going to leave 1 out. Now we're talking about the sum being prime. Okay, not just rolling a prime number. So the sum is odd or the sum is prime. So prime sums would be 2 is a prime, 3 is prime, 5 is prime, and 7 is prime. 11 is prime in this list. Correct? Those are the prime sums that are favorable to our sample space. Okay, and these are prime sums. Now we want the sum to be both odd and prime. Well, the only ones that qualify here, 2, 3, 5, 7, and 11, right? 9 is odd, but it's not prime, so we're leaving this out. So the problem amounts to the following. To do that, we need to find what is the probability that the sum is 3, or, let me actually use the word or, could be 3, or 5, or 7, or 11. We're going to leave 9 out again because 9 is not prime. Okay, the other sums are. Now for each of these, we can either get them directly from the diagram. In fact, let me copy that diagram down here, and then I'll continue on. Okay, so I went ahead and copied that down here. So let's take a look at all the ways we can roll a sum that is 3. So we can roll a 1 and a 2. We can roll a 2 and a 1, right? Those two outcomes give you a sum that's 3. How can I roll a sum that is 5? Well, 5, that would be 3 and 2, right? 4 and a 1. 2, 3, 1, 4. How could I roll a 7? A 7, that would be, let's see, 5 and 2 makes 7, 6 and 1, 4, 3, 3, 4, 2, 5, 1, 6. Those would add up to 7. And 11, we already did that one. 11, you can roll a 5 and a 6, or a 6 and a 5. And those are the favorable outcomes for the event that I just defined. Probability the sum is odd or prime. And I think that looks right. So at this point, we just have to count how many outcomes I actually circled. So I've got 2 here, right? 2, and then on the main diagonal, I got 6. So I've got 2 plus 6 plus. Then I've got 4 more circles and 2 more, so that's going to be 14 total, right? Okay, so there are 14 favorable outcomes out of 36, which reduces to 7 18ths, right? That would be the probability of the event that I just defined. Okay, so here we did use the example of or, and again, these are mutually exclusive events, the 3 or 5 or 7 or 11, which amounts to probability of 3 or 5 or 7 or 11, and we found those directly from the diagram. Okay, so we're done with this lecture, and we're done with this section on events.